So we have a question here. In the 17th century, Kepler proposed his law of harmonics for planetary motion. This law suggested that the ratio of the square of the orbital period t to the cube of the mean radius r has the same value for all the planets that orbit the sun. Mathematically, his law of harmonics can be written like that. Okay, and we've actually proved this before as well. Okay, and then it says the table shows data for Earth and Mars. Show that if for Earth and for Mars, k has a value of 3 times 10 to the raised power of minus 19 per second square per meter cube. Okay, so all you have to do is, t square is equals to k and r cube, and I can further simplify it. And if I want to find the value of k, I'm going to be doing k is equals to t squared by r cube. So I'm going to plug in the values there, and I'm going to see my answer. So I'm getting a value of 2.958 times 10 to the raised power of minus 19 second square per meter cube. Okay, now I'm going to do the same thing for Mars. And when I plug in the values of Mars that they've given me up in the table, I'm going to get a very similar answer as well. And both values are actually approximately equals to the value that they have told us to show. Okay, so that's the answer to this question. Okay, the next part says Kepler's law of harmonics was derived later by Newton. Now, Newton applied his law of gravitation to a planet moving in an approximately circular orbit around the sun. Determine a value for k by applying Newton's law of gravitation to a planet of mass m moving in a circular orbit about the sun. And using Newton's method, we're supposed to find the value of k. Okay, so how will we go about this? So we're going to be applying Newton's law of gravitation, which is F is equals to gmm over r square. Okay, and it says to us, he applied this law of gravitation to a planet. So it's a planet, and this planet will be orbiting the sun. Okay, and we can apply the law of gravitation, which is F is equals to gmm over r square. And this planet is moving in circular motion. So I can say the gravitational force is equals to the centripetal force. So gmm over r square is equals to mr omega square, where the small mass is the mass of this and the big mass is the mass of the sun. So I'm going to cancel both m's out. I'm going to be moving the r down. I'm going to get r cubed, and then omega is 2 pi by t, and that's supposed to be squared, and that's supposed to give me 4 pi squared by t squared gm by r cube. And then I'm going to move things around, and I'm going to get this as my value of k. So I'm going to plug in the value. So I've plugged in the values. They've given me the mass of the sun already. It's right up there, and now I'm going to get my answer. So I'm getting an answer of 2.97 times 10 to the raised power of 19, which is actually very similar, or actually the same as the answers we got above. Okay, so that's how we proved this. I've again shown this already, and in the videos as well. So now we're going to be going to part 3 of the question. So let's go through this. Jupiter is the most massive planet in the solar system and has many moons. Kepler's law of harmonics applies to the orbiting moons as well. However, the value of k for the moons is not the same as the value that applies to planets orbiting the sun. Makes sense? So Ganymede is Jupiter's largest moon, and Ganymede has an orbital radius of that, and it has an orbital period of that. Okay, that makes sense. Okay, let's highlight this. So orbital radius, and then we have an orbital period for Ganymede. And then we have another moon, Io, and then it has an orbital radius of this. Okay, so first of all, I know t square is equals to k r cubed. Now what I'm supposed to find is the orbital period of TIO. Okay, so let's write the orbital period of G, which is Ganymede. square is equals to k, the orbital radius of Ganymede cubed, and the time period of I/O square is equals to k r, the time period of I cubed. Okay? Now if I make k the subject in both cases, I can see that these two time period divided by the orbital radius both will be equal, so I can equate both of them. So tg square is over rg square is equals to ti square over ri square. Okay, remember that right there is for Ganymede and that one is for I/O. And when I plug in the values, this is what I get. So let's find the time period of I/O square. What's that equal to? And remember, the time period of Ganymede is given to us in hours. So I've multiplied it by 3600 to change it into seconds. So this is going to be 2.35 times 10 to the raised power of 10. And the final value of the time period is 1.53 times 10 to the raised power of 5 seconds. That's going to be your answer. Also, this is cube. Okay, welcome back to another exam walkthrough. We have got here a question from basically it's kind of like a combination of oscillation plus gravitational fields. Okay, so we have a combination of both of these. I'm going to put it in the gravitational field playlist. Okay, so it says a simple pendulum has a time period of 2 seconds on Earth. Okay, and calculate what the period would be if the pendulum was on the planet Venus. Okay, so what do we have to do here is we have to see t is equals to 2 pi square root L over G. Okay, and what I need is the value of L here. So I'm going to plug in 2 is equals to 2 pi square root L over 9.81. And then I'm going to find the value for L. And the L value is going to be 0.9936 meters. Then I'm going to find the gravitational field for Venus. That's going to be G is equals to Gm over R square. And that's going to give me 8.874 Newton per kg. And now what I'm going to do is I'm going to find the new time period if the pendulum was on the planet Venus. So 2 pi square root 0.9936 over 8.8745. And that's going to give you the new time period as 2.1 seconds. Okay, we have an MCQ. It says the Earth has 10 times the mass of Mars and twice the radius of Mars. The gravitational field at Earth's surface is GE and the gravitational field at Mars surface is GM. So my aim here is to find GE over GM, because if I move this to the other side, okay, and if that doesn't work, then I'm going to be moving these to the other side, okay. So my aim is, first of all, I'm going to find this, okay, that's the first thing I'm going to do. And then I'm going to play around with this and move the values, and then I'll see what I get, okay. So the gravitational field at Earth is G times the mass of Earth and the distance, the radius of Earth square. And then we have the gravitational fields of Mars, which is G times the mass of Mars divided by the radius of Mars. Now the reason we are taking this as the radius is because we're considering the gravitational field strength at the surface of these planets. And I'm going to divide both the equations. And this is what things should be looking like. I'm going to cancel that G out. And further simplifying it, I get this. Okay, so this is the mass of Earth times the radius of the Mars square. The mass of Mars times the radius of Earth square. And we know from the start of the question that the mass of Earth is 10 times the mass of Mars and the radius of Earth is twice the radius of Mars. So I'm going to plug those things in. And then this is what I'm going to get. So the mass of Earth has been replaced by 10 times the mass of Mars. And then the radius of Earth square has been replaced by 4 times the radius of Mars squared. The reason why it's 4 is because, remember, it's 2 times the radius of Mars, so when you square it, it becomes 4. Okay? I hope I wasn't too quick. So then you're going to cancel the values out, so they're going to get cancelled. These two are going to get cancelled, and you're going to get 10 by 4 is equals to GE over GM. So that's going to be GE is equals to 2.5 GM. And I could flip things around as well. So I could flip this up and this down and this up and this down. And we would get GM over GE is equals to 4 by 10. So GM is equals to 0.4 GE. Now look, I told you at the start we were going to play around with it and we could find the two things that we need. Now look up. If you compare, then our correct answer is A.